Record. Okay, so now we're going to share. Okay, so this is going to be a little bit funky because in order to really do some of these things, you need an add-on if you want to do some of these things. So that's what you need to remember, is that what I'm just kind of teaching you is what's the potential is, but to really do this properly, I'm going to tell you where you need to buy add-ons for Excel, because Excel is very powerful, but sometimes you need extra things. So what we're really talking here today is, in chapter 9, is about how do you incorporate risk. This is super important because why? Stuff happens. It never happens like we think. Bless our hearts, best laid plans never happen. It's always in the details and something goes awry. So let's start with our definition. If we're defining risk, what that's defined as by professionals in the field is having some sort of probability distribution around the outcomes. So in Hawaii, we do well with this concept because we're really into gambling. If you're into gambling, you understand odds. So that's really what we're talking about. What the odds of this outcome? What's the odds of this outcome? Because remember, we're forecasting ahead as many as 20, 30, 40, 50 years. If we're really on a sustainability agenda, we're forecasting 100 years. That's really the length of time that a community lives. You have grandpa and grandma, mom and dad, the kids, maybe even great grandkids. So that is usually a 100-year span, and that's really what sustainability is geared at, is that idea that that whole extended family can have the same sort of opportunities and sets of experiences among them. When stuff disappears in your generation, then that's not really a sign that we're sustainable. So risk is really this idea that we can look at probabilities of something happening. The other kind of notion that happens is we have no clue. And this is one of the things that makes problems wicked. When we really don't know what's going to happen, then it's uncertainty. And this is what causes what we call wicked problems. We can't fix them because we don't know what's going to happen. And I have to tell you that people become very unsettled by not knowing these things. So then they end up focusing on what they do know, and they get all obsessed with it. So this is one of the problems with running cost benefit. It really works best if you know the risks. And so we will talk a little bit about how you actually estimate that a little bit later. But we really can't deal well with uncertainty. So we're always trying to push into certainty, or at least some sort of idea of a distribution of options of what might occur. And so we have a lot of ways. I'm very much into a thing called AHP, where you kind of ask people to kind of make assessments, and you can ask experts to make assessment, and it can be as simple as what's most likely to happen, and how bad can it get, and how good can it get. So if you can get it on that scale, you can usually get most experts to kind of give you an impression of how bad and how good and what's most likely. So those are three options. And then we don't really have per se an exact probability, but we really have kind of like a high, low, and average sort of thing. So we can kind of relate to that. So if you don't have any idea, ask yourself, how bad can it get? How good might it get? And what do I really expect is going to happen? And I'm going to tell you what, most people lie to themselves like fiends. Most of us try to be optimistic, therefore we're unrealistic. So this is another thing that kind of gets in our way here, because we just often cannot find these nice odds laid out about what's going to happen. So this is one of the first things that disquiets everybody about risk and uncertainty in this class. So what we generally do is we would treat it as part of sensitivity analysis. So we actually have an idea of understanding how responsive the NPV is to variations in our assumptions or in the variables that we use. So that's really why we're interested in it, because we want to know, does this NPV really going to jump around a lot if this one key variable changes, or no, it's pretty stable. And as I've said before, ecologists are obsessed with this to the point of being sadistic, to where they run their models out 35 years to see if they blow up, as they call it. And that's really what we're trying to do is, does this NPV just really tank if we're off in this estimate by a little bit? If it does, then we need to know that, because we need to definitely make sure that we are as close as we can be to understanding what that actual NPV is going to look like. So if it tanks very quickly on a bad assumption, then we may want to put more energy into examining that assumption and fine-tuning it so that that NPV prediction will be more accurate. And then we want to warn the user that this thing really blows up if this number is wrong. So you want to track it, you want to re-estimate it, you want to make sure it's right on. And we see this becoming even more important when we look in the fields, and we see that bioinformatics is becoming very, very important. That's one of the reasons why it is, because we want to understand how these data sets change. And when we understand that, then we can plug that back into things like NPV, because we'll understand what climate change will do to yields, or what climate change will do to temperatures, or whatever it is that we're trying to then incorporate into our cost-benefit analysis. So this is very, very important. Again, it's very mathematical, because we have first-degree stochastic dominance in risk, which is just means, then we have second degree, which is variances, and then third degree is distributions. So again, if you hear these math words just like leaping out of my mouth, it's all about math, and it's probably everyone's least favorite topic. So that's why we have a lot of tension around this, because people just don't like math, they don't like using it, they don't like these programs, they don't know how to interpret it. Science we do pretty well at, but math is one of the things that we really get into stumbling blocks, and that's what we need to use when we do these NPVs. We really do, so it's a problem. So what we're really trying to do is get an idea of the range, and then somehow get some way to plug that range into the NPV and translate the range in a variable to the range in the NPV. It's very, very useful, because whenever that NPV becomes negative, that means we're not really meeting our opportunity cost, and that is a key problem. So we need to deal with that problem. So we have kind of different ways to do risk modeling. The thing that we usually do that's the simplest, if you take probability theory, is to do discrete probability distributions. And that's where you get a probability of this thing occurring and probability of this one, so it's all discrete. And you can calculate expected values. You just multiply the value times the probability will happen, then the next value times the probability that will happen, and on it goes. And so that's normally what we do, because that's the simplest. The next option is joint probability distributions. That works well if they're correlated, because you can do almost the exact same thing. That means they tend to run together. If this one goes up, then that tends to go up, right? And if we know how this one goes up and that goes up in the same way, then we can also look at the impact on NPV, because it's a very predictable relationship, and that's what correlated means. That means they tend to move together. And if they tend to move together, then we can figure out the absolute value of each one as the other one moves. So we're fine. The problem becomes if you're using joint probability distributions between the variable and the NPV when they're not correlated, and then you've got all these different combinations. So you would have to run every single combination to find out what was going to happen. And that becomes like a Monte Carlo simulation, where you actually go through an entire distribution and you go through 100, 200, 1,000, 3,000, 4,000 kind of runs. And then it will estimate a distribution for NPV as you run that through all the different possible combinations of variables that change. That's called a Monte Carlo simulation. It's very easy to do once you know how to do it and you have this add-on in Excel. It sounds fancy, but all you're doing is simply running simulations where all the variables keep coming in and coming in and coming in, and you do it so many times that you actually get a distribution for net present value. And you can see that, oh, it moves like this, or it goes up very slowly and then it falls down, or whatever it is. Then the user knows that this is what we're facing. So we can also then track our NPVs and see where we are on that curve so that we can do our best job to get our best NPV, which is what we're shooting for. So let's calculate an expected value. So here we go. We have the low, the best guess, and the high. So this is what I kind of suggested, the high most likely, and the low. So again, we may not know even how much things cost, but if we have this cost distribution and then the low was, we decided a probability of 20%, high was probability of 20%. How might we actually find this out? We would actually have to map real data and say, okay, so how much did these costs go up and down? So we'd have to find some real data, and we'd have to get how they were distributed, and then we could get a probability distribution and not just these three estimates. Here, this is expert testimony. We rely on that a lot. It's easier, it's faster, but it may not necessarily be better. It may be okay, but it may not be better. So it kind of depends on what data you have on your hand. You may not have a full bunch of data that you can analyze for a probability distribution. So this is just what we need. We just need some sort of variation. We just ask an expert, we're done. Like a retailer or a wholesaler might be able to give you information of how those costs have changed over time. Super simple, good enough in some cases. So then you get the expected cost. That's multiplying the probability here times the cost, just like the formulae. The probability times the cost. So the probability is 20%, cost is 50, so we end up with a $10 contribution at the low, and an MPV, after we plug it into our formula, at a cost of $50 as 86. So then you would get an expected MPV of $17.20. If you then don't plug in the 50, but you plug in the 10, then you get an expected MPV of 17.2. So then the next one is you take the $60, and that gives us an MPV of $36. Well, actually, what this is not the expected MPV at 100, it's the expected MPV 60% of the time, right? Because this is the MPV at 60, and this is NPV if it's 0.6 times 100, putting that in the MPV formula, which is different than just calculating the MPV at 60. So they're slightly different. So the net benefit exclusive of costs then would be $1.36. So that would be adding these up. So they're calculated slightly different depending on what you're actually trying to do here. It just says cost. So we don't know where that cost comes in the MPV formula. So if we had something that looked like this, then if we had 20%, it was going to be 50, and 20%, it was going to be 70, then that would be an example of the non-correlated ones, right? So we'd have to run through the expected net benefit from each combination. We'd have to run through a 20% for this, and then, you know, all the combinations where this is 20, or it's 60, or it's 20, and then it's 20 here, or 60 here. So you have to go through every possible combination. In this one, it was directly correlated just to cost. It was not correlated with benefits at all. Here, they're not correlated one-on-one. Benefits don't go up at the same time as costs go up, or benefits don't come down the same time costs go down. So they can go in opposite directions, which means they're uncorrelated. So you're going to have to run them through each individual combination. So that would be a 50 and a 70, a 50 and a 120, a 50 and a 205. Then a 100 for a 70, a 100 for a 125, and then a 100 for a 205. And then a 125 with a 70, a 125 with a 125, and a 125 with a 205. So it's a factorial set of combinations, and the probabilities would then be assigned accordingly. Like if the cost was 50, that would only be 20% of the time. So when you multiply up here, the probability times the cost, that's what you're accounting for. But you would still look at all those combinations. Fortunately, I think the homework is a little easier than this. Okay, so then we have the next concept, which I suggested, is maybe we have a data series so we could get a bunch of different observations about one variable so we know how it went up and down. say we had a price index and we took out all the effects of inflation and we looked at how the price of this thing changed over time, and we had a 20-year data set with observations every day. Well, in that case, we could actually get a probability distribution. So you can assume the probability distribution is of a certain type, such as a normal or a cumulative, or you can actually estimate them with a program called like Best Fit. You can actually put data in there and it will spit back at you what the probability distribution is. So you can estimate it with a program such as Best Fit or other software. You just run through the data and it tells you what the distribution is. It will describe it for you in either in an equation or in a shape, and then you can use that shape to move forward. Another option would be to pick something that looks similar. So you get a bunch of prices and you plot them on a graph, and then you pick something that looks close to them and you say, oh, it's good enough. So that's another option. So some risk modeling programs offer you various distributions. So you would just graph your distribution and see which one it's shaped like. So it's pretty straightforward, but it's a powerful idea to understand how a variable changes over time, or changes through, not even over time, but maybe cross-sectional data. Maybe you're doing something that touches different parts of the country, and there might be different effects of global climate change in different parts of the country, so you'll need to understand that. So again, it kind of depends. But the most common thing is this high, medium, best guess thing. That's what everybody does. Or a cumulative frequency distribution where it's between 0 and 1. So you basically are saying, okay, so you're assuming that's all going to be, every option is between 0 and 1. So you just kind of plot about how many times it was 3, how many times it was 4, how many times it was 5. And then if you put that between a 0 and 1, then you'll actually have probabilities also. That's why you're restraining it to a 0-1 scale. It will automatically degenerate to a probability. If it was 4 10 times out of 50, then 20% of the time it was 4. You did 50 draws and 20% of the time it was 4. So that's what it means. So that's an easy way to get a probability. Okay, so the next thing we want to talk about doing is simulation. And what is simulation? So simulation is basically, we have modeling programs called At-Risk. There's other ones, but At-Risk is an add-on to Excel. And what they do is they allow you to run these Monte Carlos where it will, you tell it, this variable, I don't know what it's going to actually be, but I have a probability distribution. So you put in the probability distribution for one or more variables. Again, it's difficult to do manually, but if you had it, you would put it in At-Risk or another similar modeling program, and then you just tell it to do 1,000 iterations or 3,000 iterations. So what it's going to do is going to go to that distribution, it's going to pluck a value for that variable from your distribution, and it will pluck it according to what the probability distribution is. So you don't have to manually do it, but it'll do it like 3,000, 5,000, however many times you tell it, and it will come up with an expected MPV. So that is the most likely occurrence over time, over 3,000 draws. That's what you're going to expect to get for an MPV. So that is useful. And then it also gives you a distribution of every MPV you got. So you have the expected one, and then you have how it distributes. So again, you can tell the client, well, here's the most likely option, the expected MPV. Here's the low, here's how bad the MPV can get, and here's how big it can get. What will actually happen? We are uncertain, because you don't know how many times you're going to have to actually run through this distribution. Are you going to only make one draw, or are you going to have the same distribution over the 20 years that you're running the project? If you are, then that MPV could change every year from the expected MPV as this went along, and you're not really sure exactly what's going to happen, but you have a range. So you can make your decision. If you cannot live with that loss on the low, then you shouldn't do it. If you cannot live with any loss, you shouldn't do it. Or you figure out what variables are causing this thing to be so low and try and either do a better job of keeping those under control so they can chop off the low end, or anything you can do to prevent this negative from happening. And why do we have that problem? We are risk averse. In general, we think all humans are risk averse. It's how much risk averse are they? So you notice here, we have two different options. A, which has a lower expected value than B. But B, even though it has a higher expected value, at any given time you may lose, because at any given time you may be over here to the left of 0, which means you make a negative amount, so you lose. Most people are very scared of losing. They're pessimistic on this one. So how many people would go with this one? And really, stand a chance you're not going to make as much, but you're not going to lose. So most of us are afraid of losing, and this clouds our judgment. So this is what we're talking about, risk averse. How much are you so afraid of losing that you're willing to take the surest thing at a much, much less value? That's the trade-off you're discussing. So most people are risk averse. It's a question of how much. We change on a day. Some days I'm in a risk-taking mood. Some days I'm not. Some days I'm scared. I'm older. You get more willing to take some risks and less willing to take others. So this changes on a daily basis by individual, and groups are different. Some groups, I mean, sure, the high school boy syndrome, they take a lot of risk. Even though they know they're going to lose, they'll still do it. And high school girls, I've seen them not be willing to take any risk at all, even though there was nothing to lose. So again, it depends on the person, but you've got to navigate this with clients and with yourself when you're looking at these MPVs. If there's a chance I can lose, how do I feel about that? And that's really the purpose of looking at a risky distribution, to see how I feel about the risk involved. And that's why we want to run through all these different MPVs to see how bad that is. Because when it's good, most of us will not complain if we do better than we thought. But when we do worse than we thought, then we become upset. And you see this in the stock market. They'll tell you, do not get out of the stock market after it drops. Time to get out is when it's at the high, when everybody else is coming in. You should be getting out. But we have this thing where we lost, but if we don't leave the stock market, we didn't really lose. We just sit here until it comes back. But so many of us will want to just run the other way because we lost. We just cannot stand it. So this is a real effect, and you have to be careful with clients, because some of them will not want to think about it. Some of them will not understand the risk aversion. Some of them will only want to hear certain things in their ears. We only want to hear what we want. This is a documented, researched phenomena. It's been demonstrated that people hear what they want, and what they don't want to hear, they don't hear. Crazy, but it happens. So that's really what we're trying to do, is gauge that client's risk aversion and your own personal risk aversion if it's your project, and be realistic with yourself. It's not going to come out like you want in every case. So that's just what it is. So we need to understand what kind of variations we can expect and how to prepare ourselves for those variations. And because of this, again, when it worth large sums of money, then we get really, really nervous. So this is really about risk and how we react to it. This is documented really in what we call utility theory. And again, as you get more and more money, you feel better, but each dollar as you grow, you get less and less happiness from that new dollar. So when you're really poor, that first dollar is great. But as you get really rich, that dollar is less important. So this is a problem when you're dealing with community. Because what you'll have is, if it's dominated by rich people projects, they'll act differently, right? They won't really care so much about that wealth. So they'll respond differently to projects, but when they're really poor, they really need it. So you really need to understand this when you look at your distributional effects. The different groups will respond differently. And when we're doing, I don't believe it's this chapter, but when we get into the next chapter, which is really trying to look at the impact of income on projects and income distributions on project decisions, this becomes very, very important. Because we have a lot of poor people that are making decisions, excuse me, that are counter to sustainability because they just don't have that ability to wait, and they don't have that ability to lose. If they lose, we're in deep trouble. So they're not going to take on some things that maybe might be on the surface a pretty sensible thing to do. So we have to understand that, and we have to come in and maybe protect them from that loss in order to get them to do better at adopting sustainability activities and ideas and projects and everything involved in being more sustainable, because they're really afraid of losing. And a lot of times with these sustainability things, you don't really win big. You're really making a sacrifice and bearing a cost so that the community is better off. So we really need to kind of worry about this thing and what can we do to make people still willing to do these projects that benefit people in the disadvantaged areas. So this becomes very important a couple chapters over, and we'll talk about that. So again, this chapter, it doesn't have a very difficult set of questions for you because I didn't feel comfortable having you buy these risk add-on packages, because then we'd have to have databases and we'd have to run all these homeworks, and it would really be time consuming because you have to have a lot of data to estimate a probability distribution and really try this stuff out. So I just didn't really think we had the time, given that we're moving through an entire book. So we're not going to actually do that. But if you should want to do it in a project, or if you want to account for risk, at least go with the high, low, best guess option. And most of the time you will see this. Yields is one thing in agriculture that becomes an issue, so that's often where I see it. Yield functions, and sometimes we can go to papers even and get yield functions. I recommend my students do that. So there's ways to get around it, but it really, really hinges on how does the variable change? How does NPV that involves that variable change? And how do we feel about that change? Are we not concerned? Are we very concerned? How concerned are we about the possibility of it not being greater than 1? Because we want, or being positive, we want the NPV to be positive, but occasionally maybe it won't be. So that's kind of what we're talking about. And so one last slide. Is you're really kind of showing that as you move up this kind of wealth, as you get more wealth, the response in your utility is smaller. You notice here it's increasing at a decreasing rate. So as you get more and more wealth, your increases in utility get smaller and smaller and smaller and smaller until we get to this point where your utility is maxed out. Getting more wealth is not going to make you happier. I think we've experienced this with certain, we've never experienced it, but some people maybe have. What am I thinking about? Citizen Kane, and the guy is just so rich, but all he thinks about is the sled he had when he was a kid. The last words he says at the end of the movie is the name of his sled when he was a kid. So the guy was fabulously wealthy, but thought about his sled, his little wooden sled, when he had nothing. So this is just kind of to show you that this is the utility from wealth as you move up and get more and more wealth. And then you notice when you plus H, so when we go to our high level, we increase in utility just a little bit. But when we go to the low level, here's utility minus the same amount, much bigger impact. So we get a much bigger drop in utility when something negative happens than we do an increase when something positive happens. So hence my point, if it turns out better than we thought, it doesn't seem to be a big deal. We're not really focusing on that. What we're really focusing on is losing. So you need to remember that for yourselves. right? That this will upset me. If I lose my life savings, this is going to be a big no-no. Versus, for example, oh, I might win, but that's what I really want is to make sure I have a retirement income. So maybe if I win a little bit lower, but went with a sure thing, that might be a better option than trying to shoot for the sun, the moon, and the stars. Again, it depends. You know, how sure are you that there's going to be a big loss? When you're dealing in the stock market, in general, they have long-term probability distributions. So I'm like, you know, I'm pretty sure if I sit here for 30 years that this is going to be the return, so I'm not that worried about losing unless I get in a very upset situation and make a knee-jerk reaction to a big problem and jerk my money around. But if I leave it in there in the long term, this is what I'm expecting. There shouldn't be a loss. On the other hand, for projects, sometimes you cannot get these guarantees. So you have to really do some thinking, particularly for long-term projects. What's the probability that this will tank later? Again, you need to think about this stuff because if you really look at this, when we have a loss, we suffer a much bigger decrease in utility than when we have a win. So this drop is much bigger than this increase when we have a plus. So that's really the take-home message. And the assignment is pretty straightforward. Most of it is just calculating these expected values. And there's one question about utility. Again, utility is estimated or calculated on whole numbers. So you're moving not on a line, but the utility function will be curved. So you're going to go from whole number to whole number. So you're just trying to figure out, you know, okay, so this is my utility and I can't consume part worths. So this is where I'm going to be. Because there's one question that's a little tricky. So if you have a problem with that one, email me, but it's pretty much based on the premise that you're going to try and be at a constant state of utility, and it's going to be an integer, not a partial. You can't be at partial amounts of utility. So as long as you keep that in mind, that this is a curve and not a straight line. So in order to keep yourself equal, you may have to go from this point to this point. Right? So that may be a full drop in a certain amount of utility and not just a part of utility. You can't drop part of a utility or part of a utile. So there's just one problem where that could be a bit problematic. Okay, does anyone have any questions? Because we're moving through chapter 9. I think we've got about 3 more chapters left. Yay! I won't be here tomorrow because I have to give this workshop on Kauai. We gave one today here, and we're going to do one over there tomorrow, and then I'll be back on Thursday. And Carly.
Oh, I said that sounds cool.
Yeah, good. And I think I graded your stuff, right? And
I think so, yeah. I have to go look at it. I'm at work.
I answered a question or something this morning.
Yes, the answer, that actually helped a lot. I think I have it. I'll send it in.
That might be helpful.
Yeah, I think I got it.
And Keith, you're busy, I see, doing other things.
Yeah. I got my last class tomorrow. And
don't even worry about it. It's fine. You're leading the pack, so I'm not concerned. But let me know if you need anything.
Yeah, no problem.
You're still leading the pack, even though you haven't turned anything in a little while. But that's fine.
Yeah, that's good.
And you may have something there for me to grade, maybe homework 4.
Still poking around on homework.
Okay.
Right now.
Well, at any rate, after assignment 5, then we just go to assignments. We don't have no more homeworks, and you almost don't even hardly need spreadsheets anymore after assignment 5, because we're really going to look at these special case scenarios on how do you change how you construct either a benefit or a cost. Like, how do you construct a cost when there's a probability distribution for the cost? How do you prepare that to be installed in your MPV formula? So what we really need to focus on is just how do you prepare it to go into the MPV formula. We may not necessarily need to provide an MPV per se. So we may not need a massive spreadsheet kind of layout thing. So again, they become a lot smaller and a lot more focused on specific problems relative to sustainability, such as social equity, which is a major issue. It's a problem. We got to worry about it. So we do. And that and non-market valuation, public-private projects. So we've got public-private projects. How much is the cost difference between a public project versus a private project? They're different. Public projects cost us more because we're crowding out the tax-paying private sector. We needed to be able to compute. Do we want it to be a private project? How could we get that to happen? If we want it to be a public project, that will cost us more, but that may be better because no one else will do it. So it helps us have a discussion. And then we have income distribution, social equity, and then we have market, non-market. And those are our last lectures, and then we should just be able to move along. So no questions, and I'm going to stop share.
I think that's
Okay.
it.
Okay, see you later.
Have fun in Kauai.
Bye.
Bye.
Okay, that wasn't bad.
So are those students Hawaii students or